Hello, everyone, and welcome to RNG Coalition's 2022 webinar series. My name is Leslie Dalton. I'm RNG Coalition's Director of Communications and Marketing and your host for our Wednesday webinars. Nearly every Wednesday at 1 p.m. Eastern, our webinars feature expertise from RNG Coalition members and partners on a variety of relevant topics intended to help educate about the environmental and economic benefits of RNG, as well as to promote industry best practices. Please visit rngcoalition.com to view past webinars, as well as to see what's coming up next in our 2022 series. If you're interested in hosting a webinar or have a topic you'd like to see covered, please reach out to me at leslie@rngcoalition.com anytime. Today's webinar, presented by Soheil Khiavi of Hydron Energy, is titled Gas Separations, the Good, the Bad, and the Ugly. All participants should check and make sure they're on mute. Please remain on mute throughout and type all questions in the chat. Questions will be answered at the end of the presentation. Soheil, the floor is yours.
Thank you, Leslie. Good morning, good evening, everybody. Thank you for joining this webinar. My name is Soheil Khiavi. I'm founder, president, and CEO of Hydron Energy. I've been into clean energy and clean tech since early 2000. We started working at a company called Quester Technologies and developed rapid cycle pressure swing adsorptions and other technologies back in early 2000. Later on, I worked at a company called ZBEC, and when I left, I was director of technology development there. Later on, in 2009-10, I founded a company called Inventus for carbon capture, and that was based on an invention called the L'Occitane process. The company is now called Savante and has been grown quite a lot, which I'm proud of it. I have a couple hundred patents and some publications. Overall, my degree is Masters of Chemical Engineering from Western for UWO. Thank you. So what we want to talk today about is the effectiveness of a separation process, a process, what we call gas upgrading process. Basically, upgrading is separation of molecules. That's what it is. So you have a mixture of multiple gas molecules and you want to separate, you're interested in one specific type of molecule, and that is called upgrading. And what really calls at the end of the day, the final price or cost of the process of upgrading and separation is the thermodynamic efficiency, which is the reverse of saying what is the energy for removing two gases after you mix them. So let's say you have gas A and B, methane and carbon dioxide. When you mix them together, there's an energy released that becomes a less organized or less ordered state of the gas, releases that energy. So a process would be fully reversible if you pump that energy back and you can actually separate the two gases again from each other. That would be 100% efficiency. Well, the news is that normally our efficiency is very low, very low. This plot here shows you what happens if your concentration of the pollutant gas increases over what you get in terms of second law efficiency. So at very low end down to ppm level, we are talking about less than 0.1% efficiency. And then when you get closer to about 10% or so, then you're at 10% efficiency. So most of the gas separations and upgrading technologies out there, they are in the range of single-digit efficiencies. Compared to a ideal situation that you would separate the two gases in a reversible fashion. And when you go higher and higher than that, then it becomes again difficult. The reason that 100% pollutant doesn't mean 100% efficiency, because now you have to fight the other end of the curve, which is And now it's very difficult to remove very small quantities and purify the methane. So that's why this graph is really important to show everybody that most of these processes, the reason they are expensive is simply because they're not efficient. That's all it is. So on the next one, I'm talking a little bit more about what is the upgrading process and methods you've been used. So if you look at let's say a process for separation or upgrading a biogas, first thing that you need to consider is what is your feedstock and what product you need. Those are the two boundary conditions you need to understand. So for a fully saturated or fully wet, basically 6 to 12% of the biogas is water, if you consider that by weight. And what happens is that if you want to first remove or separate the constituents of the biogas, you need first to drop that water, the drying step. Then there is a nasty component there, which is H2S, that is quite dangerous, and they are in the level of 1000 ppm average, so that needs to be removed. Normally, the biogas is at ambient pressure, and about half and half is carbon dioxide and methane, with all the other impurities that I just mentioned, water and H2S. And the off-takers normally would say, well, I need certain purity for methane because, first of all, the biogas, the renewable natural gas, which is the purified or upgraded biogas, has to meet the Wobbe index or the thermal basically value. And that relates directly to concentration of CH4. And then, of course, you need to get rid of nitrogen. If you have too much nitrogen, then that becomes diluted and has no heat value. That's why landfill gas is a lot more difficult than a biogas, anaerobic digested biogas. So once you know what is your input, what is your output, then you need to figure out what I'm going to use to do the separation. So in general, there are separations based on physical separation, and then there's also separation based on absorption technology. The physical separation, we're talking about membranes and cryogenic systems. So these are based on thermodynamic. There's no relation there with any gas reaction. But then on the absorption side, you're talking about either adsorption or absorption. This is when you're dealing with a interaction between a species, a surface or a functional group or another molecule with the gas component that you want to remove. So that's why you can distinguish the two. One is physical, the other one is more into a reaction or chemical process. So now I'm going to go through each of these different technologies or methods on the next slide. So first one, we talk about the physical separation is the solvent separation. And this is the easiest one, I would say, from process point of view. So it's based on solubility of carbon dioxide. So if you have water, if you have PEG, basically you can dissolve carbon dioxide. And all you have to do is that to cool it down and then to regenerate it again back to heat it up. So it's a two-stage process. And in order to get the highest amount of solution of the carbon dioxide, you need to increase the pressure. You know, when you open a soda can, there's this pop sound because it's pressurized, because you need to push all that carbon dioxide in. And also when you keep your can of soda cold, it actually keeps more carbon dioxide in. Same way here. So you have a high pressure, low temperature, you get as much as possible carbon dioxide in. And then later on in a stripper column, you take that saturated solution and heat it up to release carbon dioxide. So very simple process. And this process has a good side, which is, first of all, you remove CO2, but also you can remove H2S. depending on what kind of solvent you use, of course, and is effective in terms of meeting the RNG specification, as long as you don't have nitrogen or you're not dealing with landfill gas. Also, one good part of this process is that you do not need to dry your biogas down to very low dew point because you're using actually water here. The bad side of it, of course, is that if you want to clean this up and polish it, remove the oxygen and nitrogen, you're out of option. You need to add another process there. And of course, based on information that is everybody probably who has experience with these processes, that they break a lot because the contaminant, which is you form basically a corrosion and contaminations that you have causes corrosion, which is taking the life, basically the life of these plants down. And the promise was that these will be very low capital plants. And that means that, well, you're using water, so you need just to use very cheap material. You don't need to have a very high grade stainless steel or anything like that. But actually that was proven the other way, that no, actually the contaminants and the corrosion is calling for a better or more expensive materials for construction. So, but it's a good process. And the next one, as you can see, what have been done is that people kind of walk away from this liquid process and then look at more like a membrane type separation. So membranes been around for many years and have been used in many industrial applications. But then the polymeric membranes give you this great CO2 selectivity over methane, so you can separate by permeating this carbon dioxide through the membrane wall. So these are very fine tubes. They look like very fine tubes bundled together, and when you pass the biogas through under the pressure, the carbon dioxide diffuses through the membrane wall and gets gathered outside and then gets released from the shell side. And then your methane, the clean methane, kind of goes through the system. So it's a simple, no moving parts. You don't need to worry about corrosion, erosion. You get good methane recovery. The membranes initially weren't that great. Now, with the polymeric membranes, they tailor it exactly to the right pore size. So they get quite good methane recovery. But on the bad side of it is that their membranes, they're fragile, they can easily get damaged, although the early versions damaged a lot easier now. They have been improved quite a lot. But then the performance decreases over time. The high pressure, the pinholes gets generated in the membrane wall. You have cracks. There's all sorts of defects that happens. You cannot have a perfect membrane production in large volume. There's always defects. Everybody knows that. And then it's about the life expectancy of membrane and the defects, how it's going to be progressed and how you're going to start losing recover your purity. And of course, like many high pressure processes, the energy consumption for the compressors are massive. So you need to take all that carbon dioxide and methane and compress it. Of course, at the end, you use that pressure from methane for your, let's say, pipeline, but the pressure that exerted to carbon dioxide is lost through the work that happened through the diffusion up through the wall of membrane. So, as I mentioned, the oxide is fragile and expensive to replace. Everyone knows about the cost of membranes, and there are not many options out there, but they're doing good job. I agree that this is a very good, promising technology for the future. If it could work at a little bit lower pressure, would actually save a lot of money. But then when you drop the pressure, then the selectivity drops because you have to open the pinholes and membrane. You have to open the pore size. So it's a fight, optimization fight here that happens between the capital cost, operating cost, and then the purity that you get under recovery you get. So this is where they settle currently. Expensive to operate and expensive in terms of capital cost. Now, on the other side of it, you're dealing now with something else, which is chemical solution. In order to get that carbon dioxide out, you saw that in the previous slides, we relied on solubility of carbon dioxide. Or next one, we relied on diffusion and high pressure to push the carbon dioxide through the pores. Now you're talking about a totally different animal here, and this is a chemistry. So there are materials, solvents, the chemical solvents, that they basically react with the carbon dioxide. And you don't need to be at very high pressure, or you don't need to be at very low temperatures. They are designed for the removal of carbon dioxide. So the process of sour gas treatment has been around for many years. Oil and gas upstream use the process of using amines for sour gas treatment for many, many years. So some of the natural gas that you have in your pipeline is actually coming out of the process, similar process happening in upstream oil and gas industry to clean up the sour gas. So the same technology has been adapted for the biogas in this case. So you're using a solvent. It's a chemical solvent. So that's important. It's a chemical solvent. So that means that you have a chemical plant in your farm. And it's a two-step approach, as usual, is that it's a cyclic batch process. So you take one column, and with the low temperature and slightly high pressure, you start pumping the CO2 into this, the biogas, and then CO2 gets absorbed or reacted with the amine groups. And then later on, you take that amine, move it to the next column, and you regenerate it with high temperature. Normally it's done through reboilers, and they use steam and reboilers to heat up the solution in the heat exchanger form. And this process is a great process when it comes to recovery. It's got a very good recovery. And also you can actually remove not only CO2, but also you can remove H2S. So H2S is not going to hurt this process. It doesn't mean that you need to remove the H2S, because the H2S will end up with the CO2 if you do so. Normally people clean H2S out with a different technology before that, but more or less H2S won't damage the process, and it won't slip. If you got some H2S going through the system, it won't actually run the other end. But for nitrogen and oxygen, you need polishing. For nitrogen, you need the polishing step because it doesn't remove the nitrogen. Also, it's a chemical plant, so it doesn't scale up very well. Can't really make them too small. And when it comes to the energy consumption required, the high energy consumption for regeneration has been famous energy sucker there. You got a solvent that has amine in it, and that solvent is the carrier. You need to heat up that solvent, and again, to cool it down. That is the boat anchor energy there. That is going to remove a lot of your second law efficiency down. So what you do with this process is that you use it when you need it. It's a good option, but you need to be very careful about the energy consumption. The solvent thermal cycling counts for a large portion of that energy, and you need to make sure that you have that energy in your budget operating costs. So if you take this process and then say, well, what is the best work between these two? You got physical there, all the way when we talk about thermodynamics and solvent process and membrane process, and then you got the chemical all the way on the other end of the spectrum, which is amine groups. So what is the work between the two? Well, the work between the two is this process of pressure swing that we had it for a moment in the next slide. Yes. So the pressure swing process is a cyclic process and it's a batch process. Like the other process that I mentioned, you got an inventory of a material that has the pore size distribution and also the affinity or selectivity toward carbon dioxide. So a little bit of both of the chemical solvent and membranes is in this solution down into physics level. So you got a packed bed full of adsorbent, and that adsorbent is a could be amorphous adsorbent, could be a zeolitic adsorbent, or could be a molecular gate, and so there are different options out there. And these options gives you the tools you need in your toolbox to exactly tailor make your process for your feed and your desired product. So that other ones, are kind of solid fixed membranes, is you got what you're gonna get, and it comes membrane, you go and buy it. But when it comes to the PSA, you can actually tailor make it. You can have different layers of adsorbent inside of these vessels, and you can have different type of cycle, trade-off between recovery, purity, a lot of more engineering involved, of course, but then you can optimize your solution. There's no liquid handling here. And also you can remove nitrogen and oxygen because, as I mentioned, you can play tricks with the chemical, with diffusion coefficients and the kinetics to remove the nitrogen and clean up the landfill gas in the liquids. On the bad side, you can see that this process needs high pressure. So you need to use the pressure, and after you gather all that carbon dioxide inside of your adsorbent or nitrogen, you need to remove that. And how you remove that? Well, you pull deep vacuum. So these are transambient processes, and also gives you the low recovery because of something called selectivity. So that means the flip side of a coin of having this tailor-made process is that you are going to lose some of your methane because no material here is going to act like a chemical absorption. It's not going to be 0 or 1. It's not going to be either reacts or doesn't react. So methane is going to be, to some extent, attracted to the adsorbent, and that is called the recovery loss here. So you can design this to go to up to 90-95%, but to go to 99.9% recovery, good luck. It doesn't work that way. I have designed PSAs for a big part of my career. They're versatile, you can play with them, but then always the recovery was an issue. And also, of course, the high energy demand you need for compressor and vacuum pumps is a, in some cases, showstopper when you look at it. But nowadays, with the booming of renewable natural gas market, I think it's a good option to go after this. So you can still absorb the high cost and maintenance of the system. So this system is using solenoid valves or array of valves to switch between those beds. The more number of beds you have, you get better recovery because you can devise it in a way that you can recover as much as possible that methane that's got trapped in between the gas adsorbents. But on the other side is that these valves and this number of the vessels is going to increase your capital cost and some operating costs due to the maintenance of the valves. So how we solve this problem? Back in early 2000, we came up with the rotary valve when I was working at Quester. And the rotary valve is basically is a template for the cycle. Aside from that, it's rotating. First of all, When you're talking about a cyclic process, the best cyclic process is a circle. You go around, so you rotate. When you put the valves in the array form, click, 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 like the last slide you saw. So the valves, they go through, and then you have to restart, go back to the beginning of the line again. Well, what we figured out, well, you just put in the circle, okay? That simplifies. And the second thing is that all those valves can be actually simplified in two valves, one on the light end, one on the heavy end. The light end valve was dealing with the product, the clean gas, the equalizations, then the heavy valve was dealing with this feed and exhaust. So two valves replaces over 50 solenoid valves, and then you can increase your number of vessels in order to gain as much as possible recovery. So the good part of it, no liquid handling. Same as previous, and you don't deal with the chemicals. And you can tailor it, same as previous one. You can design for removing nitrogen and oxygen, same as the other pressure swing adsorption. But what is here added is that now you have a rotary valves that reduces the cost, capital costs and operating costs. So it gives you the capability to increase your recovery by adding number of the bits without breaking the bank for the basically rotary for the cost of the solenoid arrays and controls. The ugly side, the same as before, high energy consumption. So that's what is sold nowadays. I mean, I was proud to say that the product that Xebec is selling is the early work of is the final kind of version of the early work we've done at Quester and later on at Xebec when I was there. So now, how we solve this problem in terms of high pressure and high vacuum, the consumption of the energy. What is the solution for that? Because everything is great here. The only problem is that you still need pressure and vacuum, and running a compressor and a vacuum pump is a big part of this cost of this plant. Everybody knows. So what we came up with, I'll show you. Next slide. All right, so first of all, we look at what is the alternative, and the alternative to the pressure swing and still dealing with the temperature with the adsorbent is temperature. So you don't use the pressure, you use the temperature to give you that cyclic capacity that you require. So it's a cyclic batch process and using temperature as driving force. But when you look at industry standards for the TSAs or temperature swing adsorption, they are all going through the pressure swing also because the lack of capacity of adsorbent. They kind of improve the capacity by just pushing more pressure into the material. So all the benefits that you saw in the last slides applies here. Is no liquid, first of all, it can be tailored, second of all, and then is used for natural gas drying. Everybody knows about this process for natural gas dryers. But the bad side is that you still need the pressure. And it requires high temperature for desorption. So you don't need any more the vacuum, but you replace that vacuum with temperature. And still that is an energy drain, basically. So how we can actually now fix the problem combining the previous processes and with this process. So what we figured out is that to get rid of this high energy demand for the pressure and the energy demand for the regeneration, the better solution would be combining the adsorption process with a process or material that can have higher affinity or higher capacity at low pressures and require lower energy for regeneration. So that is on the next slide. We show how this is done. So the first application for this is the Veloxyton process. I'm the inventor of the process. The first application we chose was carbon capture. And carbon capture because it's a process that deals with all the problems that you saw here and we have today here with renewable natural gas. You want to upgrade the gas, clean it up. In this case, you wanted to get the CO2 out. In our case, we want to get the CO2 out also, but we want to have fuel. In the flue gas case, you didn't have to have a fuel, you just need to remove the CO2. But the problems are the same, which is do it at lowest energy, lowest cost. So how we do it? Well, we use this process, the Bloxton process. First of all, is enjoying the rotary valves, but then rather than using adsorbent beds, they beaded adsorbent beds, we use this structured adsorbent. The structured adsorbents, basically, they are immobilized version of adsorbents that you can run them at totally different fluid dynamic regime. So it runs on the laminar flow. It reduces the pressure drops by order of magnitude. So you can run it at low pressure, the process, without the need for high pressure. You can remove the gas and clean up the CO2. The process was designed for flue gas, as I mentioned. So although you get the higher throughput for better contact between the gas and the material using the structured adsorbent, you get higher throughput. You require lower regeneration energy because of the form of the structures, you don't have energy loss. You don't need to wait too long for the heat to diffuse in. And it operates at ambient pressure and requires very low temperature to regenerate. But this process was sensitive to contaminants, and it was quite large, difficult to seal these valves with large diameter. So it's not really a good candidate for dealing with natural gas or hydrogen, any combustible gases. But it's a good start. Removing carbon dioxide, we can remove carbon dioxide. But it's mainly was for post-combustion. So what we did is that in the next slide, you will see what we did is we took that process and we adapted the process and we changed the process. We adapted the idea of using rotary valves. Of course, that is a very good option. We adapted the use of structured adsorbent. So there's no beads in these beds. They're made of structured adsorbent. But then there's major change also there. That is what we figured out is that if you have a stationary beds with rotating valves, the chances of the leakage and the chances of basically having problem with the flammable combustible gases goes away. So risk reduces using the architecture that you see, stationary valve, stationary beds and rotating valves. And also what we see here is that the material inside is actually what they call solid amine. So we took advantage of what is inside of the human body for the removal of carbon dioxide. There's an anhydrase, which is amine type, functional group that's connected to a long protein. Well, we don't have a protein here, but we have a polymer, and that polymer acts like a substrate or a holding framework for the amine groups that are solidified inside of this molecule. So it's a plastic made of amine. It can absorb about 50% of its weight when it comes to carbon dioxide and can get regenerated at very low temperature. We're talking about at 80 degrees Celsius as well as 80 degrees Celsius to remove the carbon dioxide regenerated. So suddenly we have a solution here that we always dreamed about it, which is getting the process working at ambient pressure, so you don't have to compress your biogas. After you get the renewable natural gas produced, the methane, the biomethane, then you compress it. So that would cost half in terms of your compression costs, whether there's a capital or operating cost for that compressor, because suddenly half of that gas, which is CO2, it no longer needs to be compressed. So we remove that at low pressure. there's no deep vacuum required, and we use just the waste heat from the compression train and the remaining of the process to regenerate the process and to regenerate the media to remove the carbon dioxide. The bad side of this is a new product. Although we can cover a wide range from 120 to 2,500 cubic meter per hour with one unit, of course, the unit scales out. So it's not this unit here you see is the size for 120 cubic meter per hour. It can scale out to up to 2,500 and still is a lot smaller than all other processes out there. But then it's a new product. So normally in any industry, new products are always associated with some level of risks. So that's the bad side of it. And we are actually learning that. And also for the nitrogen, the first version of this, we are not going to use this for a nitrogen removal. So the process only removes the carbon dioxide. For the nitrogen removal, you need a secondary process to remove the nitrogen from the landfill. So that it will work very well for anaerobic digesters, though. And the ugly part of it is the lack of our experience. Just the field experience is not there. We're building a small, the size that you can see here in the picture, a narrow down beds version of it that's going to be installed this winter, and that will be our first field experience. But we have a lot of experience when it comes to remove carbon dioxide from flue gas. So now I want to talk about overall what we just covered in this presentation. Thanks for your patience so far. So it's important to look at all these processes. There's no like the best one out there or the worst one out there. There's always a best solution for the problem that you have, but doesn't mean that that is the best solution for somebody else's problem. So it depends on what you have, what's your boundary conditions. You need to figure out what kind of process you need for your upgrading. So the contributing factors for this would be, what's your biogas source? Is it coming from an anaerobic digester? But it's coming from landfill? It's coming from wastewater treatment plants? Depending on what source you have, you need to figure out what kind of industry you're at, what kind of contaminants you're dealing with. If you're in the farm, most of the cases that I know, like amines and the farms, kind of, at least in the past, it wasn't that. It's a chemical plant, so you don't want to have it in your farm. But things are changing. They get a lot better in terms of their safety. But the other thing that you need to consider, of course, is the cost model. So you need to see how long you need to amortize the project over what period of time, what's going to be your capital cost versus your operating costs. Some projects, they can absorb a lot of costs at the beginning, so you go with higher capital option with a lower operating cost. So you need to figure out which is the best in terms of your cost model. And of course, the durability is a major issue that all these processes, they have durability issues, especially if they're not handled properly. And if they operate properly without having hiccups, without doing anything wrong with the process, then it will be durable for as far as the producer or manufacturer is guaranteeing. But some cases, these are sensitive to operating regime. So operators are important dealing with these processes. And the scale up project is very important. If you have a very small scale project, you need to look at the footprint. You can't have something like a large amine plant in a small facility. So those are the things that you need to pay close attention when it comes to the scale of a project, how you can grow in future. Maybe you have a plan to grow the site, whether that's going to be a good solution to go with something that can expand in future. And also the offtake is important. Of course, you need to make sure that consumers needs out there. it's been taken care of. For example, for the landfill gas, I know a lot of people, we're not, this is anaerobic digester and the biogas. We're not talking about landfill, but I'll give you an example of a landfill. There's some nasty material there is called siloxanes. That these are most of the softeners that they end up in the sewage, end up in the landfill. The creams and the material used for softening. And they are basically silicone and some organic thing connected to it chemically. And when they burn whether it's in the final burner or in their engine, they create these glass particles, nanoglass particles that basically corrodes the material, the moving parts. So those are important things to consider, like what is your feedstock, where it comes from, and what you need in the product, what you don't need to see in the product. Special attention to the carbon intensity goals, and then the maintenance requirement, of course, is a key. That some of these processes might be very cheap at the beginning, but then they require constant maintenance. So you need to see whether that is a good match for you or for someone else. So that, in summary, these are the things that I have learned over time since early 2000, being in the industry of gas separation, and I'm glad to be here and to talk about my experience with you. Thank you very much.
Thank you so much, Soheil. Allison, there are 2 questions waiting in the chat. If you want to unshare your screen and we can see you on video, and then if you could go ahead and read the questions out loud. And Soheil, if you'll take the questions, that'd be great.
Yeah. Sure.
Thank you.
Hi, everyone. Good morning or good afternoon. Yes, there's 2 questions right now in the chat. If anyone else has any other questions, please be sure to add them there. So the first question for you, Soheil, is the multi-swing system susceptible to contaminants, such as other gases or small particles?
Yes. Thank you for the question. That's a good question, actually. So the multi-string system, like many other systems, almost all of these systems that you saw were susceptible to some level of contaminants. And when you talk about contaminants, it varies from process to process. So, for example, as I mentioned, the H2S, when you deal with a process that using the chemical absorption, H2S is not considered to be damaging or contaminating. But when you deal with a pressure swing adsorption, H2S can stick quite hard to absorb, and especially if you use some amorphous materials, some carbon molecular sieves, they could be quite nasty and will, over time, degrade the performance with the pressure swing adsorption process. In our case, with the multi-swing, because we are using what I call solid amine, post-amine, the H2S is not in the matter. It's not an issue. Of course, we want to remove the H2S before our process because we don't want H2S to end up with the carbon dioxide and it gets regenerated for that reason. But if there's any slip of H2S, our process will capture that and then we'll release it with the CO2 carbon dioxide outside. We are working future versions that the H2S will be actually separated by our process also in a separate container, but that is for future. In terms of particles, when we deal with flue gas, with the parallel passage contactors or structure absorbents, we did a lot of work on DP95 particles to make sure that the particles doesn't block the channels. The channels are tight, but they are still order of magnitudes larger than the particles that normally we call them particles. About the channels are north of 200 micron, and the particles easily down to 5 micron even can actually go through the process without getting clogged. So there won't be any susceptibility to the particles also. Although when you talk about particles in the biogas, what does that mean is different from case to case. So if there's any more clarity that the question the person who asked it maybe can provide later what type of particle exactly they're looking for, I can give more clear answer based on that. Yep.
Thank you, Soheil. So the second question in the chat actually builds off the first one a little bit, and you may have covered some of it already, but the question is, how does this perform when exposed to H2S, as well as various organics found in landfill gas, such as xylene, acetone, MEK, etc.?
Sure, that's a good question also. So remember when I was talking about the PSA slide, the pressure swing adsorption slide, I was emphasizing clearly on the point that these are tailor-made solutions. So you can actually take and use different materials in order to capture different impurities. And that's what we carried that kind of capability with the multi-swing process. So the multi-swing process is a process that is not just relying on that solid amine only to remove the carbon dioxide. If you have impurities, let's say that you have xylene or acetone or MEK, other impurities that they are in the landfill gas, the adsorbent of the material that needs to be present there to remove that particular gas could be actually tailored into the process. So we have layered adsorbent solution in the form of a structure. In fact, we worked in the past with some separations for using similar technology for chemical polymer separations. So as long as in the gaseous phase, you can actually, in fact, separate the gases. Now, what is important is to mention is that's an additional work and additional cost. So when we say that the multi-swing process is very low cost process, we're talking about the base case when you're dealing only with the removal of CO2 from anaerobic digesters, and which is tolerable also to H2S. When we start talking about adding other factors into the game, including the VOCs and other organics, and how our process can actually separate those also, of course, can be done. In fact, we have designed and invented this process to be able to do those kind of separations. But each of those gas components you add a little bit to the cost of the separation, which is not a prohibitive factor, but it's something to be considered when we ask questions like this. Thank you.
While we're waiting for additional questions to be put in the chat, which we highly encourage, I received a question over here that I wanted to ask, and it's, you mentioned the performance of membranes changes over time. What causes this, and what is the life expectancy?
Okay, yeah, that's a good question. So something that about membranes always I was interested in is that what is the true driving force that causes these separations happening there? Of course, there are membranes that recently developed for other applications that they're using, they call sorptive membranes. So they're using affinity of absorption or chemical reactions to help with the separation. But the type of membranes nowadays used in industry in the wide range is working based on pressure. So there's the amount of pressure which is behind the membrane to improve the transport phenomena of diffusion of a component A from B. It is the driving force is the pressure, and the pressure, the greater the pressure, you get better performance from this. But then the penalty you pay is that all of this causes fatigue in the membranes matrix. And like any other physical separations, you need to consider that in terms of your endurance and durability. When you have too much pressure, you have these manufacturing defects that over time start showing itself, developing pinholes and small cracks in the membrane and dropping the purity. So normally what happens is that they keep changing the process condition, trying to compensate that with operating it at different regimes. But then when you start compensating that with changing the operating conditions, then you're putting actually more stress on the membrane. So overall, you start losing, it's kind of a downhill from there on. So what really causes is manufacturing defects that is there. You can have membrane that has the minimum of these, but then the cost is higher. It's the way that they're produced. I'm quite familiar with the production, how they're doing it. Did some of my work earlier on membrane. So it's something is there that you can't really do anything with. Exactly the reason that is a low cost membranes production is that you have those issues. And overall, after time passes, you get more and more of these defects that takes a hit on your recovery and the purity. And that what is causing normally with the membranes in the industry, that what we call them aging. So there's no remedy for that. It's just you need to replace after a while. And then when you replace it, of course, you need to consider the cost of replacing. Thank you.
Great. Thank you for that. I just wanted to let everyone know we've got about 10 minutes left. So if you have questions, please put them in the chat. And Allison, there is a question in the chat waiting for you.
Thank you, Leslie. Sorry, I was muted. The question in the chat now, Soheil, is, does the rotational valve require additional maintenance compared to the traditional systems?
Thanks, Allison. Yes, that's a good question. The rotary valves are designed actually to deliver low maintenance solution for switching the flows. That's the promise of rotary valves. And of course, like many of the early trials, we actually were doing exactly opposite. Back in early 2000, the first valves that we were working at Quester, we run into a lot of problems, and they were more related to the engineering. So after a while that we figured out all those problems and re-engineer and did proper engineering design changes over time, the rotary valve design and the technology got quite mature, and we had very little problem with them since then. And the maintenance of the rotary valves mainly relates to the tear and wear, the wear basically of the seals. So there's a seal face that rotating and is rotating and pressing against another plate. That plate is properly selected for the right tribology. So there's a proper friction between and the control level of leakage through the valves. That gives you the best solution in terms of your life expectancy of the rotary valve and the maintenance costs. Normally, we design the thickness or the amount of the steels that is going to be worn over time in a fashion that this will last 5 years or even some of the designs up to 10 years of operation. If everything works per plan, let's say that if you have some particulates in your feed flow and is not properly captured or is not properly removed before going into the rotary valve. And that can cause a damage on the surface. You need a technician to go there and then change it, fix it, repair it. That's not what I call a normal maintenance. That's what I call failure on upstream of that design. There was a filter that failed. So it has to be done proper HAZOP to make sure that the operability of the process remains intact over the life expectancy. Overall, the life expectancy of rotary valves are a lot better than the poppet valves, simply due to the action and the reaction forces. When you look at the poppet valves, there's a vertical force applied. So you got sealing forces working against, and then there's the impact, then there's a removal. And all of that goes away with the rotary valves. All you have is now just a rotating, continuous rotating motion. And even in the high-speed valves in industry, Flowdyne and some other companies, they're using for the very high-end valves, they're using the rotary concept rather than just a puppet or just on-off action. So it gives you, in fact, you better life expectancy over normal valves. So our experience also been the same. After we solve all the kinks and all the issues, the rotary valve remains a very good valve solution for not only this gas operating process, but also for other gas operating, and also even for some of the liquid process can be used. So it's a lot better than traditional puppet valves.
Great, thanks, Soheil. We have another question in the chat. This question is, what is the methane recovery which can be achieved with the multi-swing system?
That's a good question. So the methane recovery of multi-swing process is very similar to, a little bit actually better, I would say, compared to amine processes, where we're talking about the numbers that we achieved in the field with post-combustion carbon capture was at 99.5, 99.6% recovery of the carbon dioxide. And we took the same number and we did tests in the lab for methane. And we have similar results. So we're talking about 99.5 and higher. So our intention is that to start, when we roll this product out, we guarantee a 99.5% for the methane recovery and the higher. So that is quite high compared to other technologies out there.
I think we have time for one more question, and I'm going to read one from over here, and it is, what was the driver for the rapid cycle temperature swing technology? Can it be applied to biogas upgrading?
Yeah, that's a good question. So the rapid cycle temperature swing technology is, as I mentioned, when you look at a pressure swing technology, you have a problem that you need to waste a lot of energy on pressurizing that all carbon dioxide. So when you go to the temperature swing technology, you kind of walk away from that problem, although you still need some pressure because of the materials normally don't have the proper uptake. But then with the temperature swing process, you go away, you actually avoid the pressure issue. So now you can operate at the right pressure, at atmospheric pressure, and the region using temperature. But the problem with the temperature swing process is that it's not fast enough. So we came up with this process called rapid cycle temperature swing adsorption. I call it Veloxitem, which was for carbon capture. Initially, we developed this process. And this process gives you the temperature swing. So you no longer need to deal with the pressure, but also your throughput is now high because the cycle speed is orders of magnitude higher than a normal temperature swing. So we do a cycle every minute. Normally, the temperature swing cycle is in like half an hour or 1 hour. So we do in 1 minute, one adsorption and desorption cycle. So that gets transferred to the biogas. Now you have a high throughput process that works on atmospheric pressure and it gives you the highest recovery compared to water. So this is basically the ultimate solution for the biogas upgrading. That's the way that we can say that we can cut the cost down by 50% compared to other technologies. Thank you.
Perfect. Perfect timing. We are exactly at the top of the hour.
Thank you.
So we have reached the end of our webinar. On behalf of RNG Coalition, I'd like to thank Soheil and Allison, as well as our audience. A recording of this presentation will be made available later today on rngcoalition.com if you want to rewatch it, or if you know anyone who wasn't able to attend, that's a perfect place to check it out. So I look forward to seeing everyone next week at 1 p.m. Eastern. And thank you again. And I hope that you all have a great day.
Thank you.
Thank you very much, Leslie, and everyone else as well.
Thank you. I appreciate it.
Thank you. Bye-bye.
Bye.